Okay, so we have just talked about the electrical field E, and now we want to talk about electrical energy E. This is the reason why I said it was pretty important to use a cursive capital E for electrical field, and then this kind of an E to represent electrical energy. And then the official metric unit for energy is called the joule, which is given by a J. Now remember, you do get to use a note card when you take my exams, so it would be a very good idea if you can't memorize all of this stuff to, on your note card, to have a list of all of the different quantities, and then their abbreviations, and then their metric units, so that you don't get mixed up with all of this stuff. So the idea is to try to understand some of these concepts and not to get too bogged down in the formulas and all the numbers associated with it. So now we want to talk about how can energy be stored electrically. And so before we get to that, let's talk about how energy can be stored gravitationally. And so that's going to be a dam. So let's pretend that you had a river that was flowing down here, and then you put in a dam. So that, okay, so here's our dam, and then what's going to happen is that this water is going to start to pile up behind the dam, and it's going to go up to a certain height. Now, the water has mass m, okay, it's in a gravitational field caused by the Earth, and so therefore it gains energy as it's being lifted up. Now the type of energy, which we're going to get to later when we talk about energy, kinetic and potential energy, but the energy that it has is called potential energy. It's the energy that it has potentially to be able to do something. So if I take this pen and I lift it up, you don't see the energy in it, but it really does have energy. It has potential energy, gravitational potential energy. If I let it go, okay, then it turns into kinetic energy as it starts to fall. So you can store energy in the form of gravity. So what would be a similar device that would store electrical energy? And so this is going to be called a capacitor. And so a capacitor is, all it is it's going to be two parallel plates. Sounds like a test question, doesn't it? So be able to explain what a capacitor is. It's going to be two parallel plates. All right, then what we're going to do is attach it to a battery. So that in the picture there, I have the positive thing on the top, and then I have the negative on the bottom there. All right, so I'm going to attach a battery. By the way, this is the symbol for a battery. You should know that for the exam. And then we'll take a wire and we'll attach it to the top part of the capacitor. So what's going to happen? Well, a battery is chock full of electrical charges, and it's going to be the electrons that actually move. So electrons are going to come out of the bottom part of the battery, and they're going to flow over to here, and then you're going to start to have negative charges appear on the bottom part of that plate. Okay, now the charges, though, they can't go back to the battery because of this open spot right here. So that negative charges start to pile up. But what do we know about conservation of electrical charges? So you can't just have negative charges like that without having an equal number of positive charges on the top. So positive charges begin to develop on the top part, and negative charges develop on the bottom part. Okay, now what would happen if we took a teeny tiny positive charge and we put them in between the plates, what would happen to it? It would be attracted to, opposites attract, so it would be attracted to these negatives, and like charges repel, so it would be repelled by these positives, so it would go down like that, and we would have a series of arrows going down in between those two plates. Well, that was the electric field. So here's the electric field that starts to develop inside of the capacitor. So we could say that an electrical capacitor stores what? Okay, it stores electrical charges. We could also say it stores electrical energy, and we could also say it stores the electric field. So all three of those things are going to be stored in the plates of a parallel capacitor. Now what's really cool is after that thing is charged up, you can take the battery out. And now that is a charged capacitor. And now let's say that you want it to do something. So maybe you want it to operate a flash bulb on your camera. So then all you got to do is now these wires, let's connect them to the flash bulb, and the electrical charge is going to drain out of the capacitor. It's going to go to the flash, it's going to make it flash, and so the energy that used to be in here is going to be turned into light energy. Conservation of energy. You can't create or destroy energy. So the energy that came out of the capacitor could go into the making the flash bulb go off. So capacitors can be dangerous. So once a capacitor is all charged up, it tends to stay charged up for a very long time. And if you happen to do this and grab a hold of both ends of that capacitor, it's going to discharge through your arm, through your heart, and then back through your arm, back to the other side. So old-time TV sets, when it used to break down, they actually had repair people that would come to your house to repair your TV. And so they would unplug the TV, and they thought they were being very safe, and they would take their metal screwdriver and they'd be poking around in there, and sometimes they would get a painful shock, if not electrocuted, by one of these capacitors discharging into them. So you got to be kind of careful with capacitors, but they're very, very useful. So they're a device that stores electrical charge, the electric field, and also electrical energy. Okay, now in the same way that you could take a charge Q and put it into an electrical field, and you would feel an electrical force, there is another formula that goes with energy. And so this time, if you this is going to be called electrical potential, and it's going to be given by the letter V. So V as in voltage. But don't make a V like that, because we're going to use that to stand for velocity, for speed. So let's use a cursive capital V. All right, so this is my symbol for a cursive capital V. That's going to stand for voltage. Another name for that is electrical potential. So I'm only going to use electrical potential like once, and then afterwards I'm just going to call it voltage. What do you think is the official metric unit for voltage? The volt. So that's going to be a capital V. So volts, that's the unit for voltage. And voltage of a system is going to be related to the energy of the system E, and it's going to be related to the amount of charge Q in the system. And so there's the formula, equation 20.3. Voltage is equal to energy divided by charge. So if you take a charge Q and you put it into a voltage V, it's going to have a certain amount of energy E. So let's try a word problem that is going to go with this. It says that a 9-volt battery produces 100 coulombs of electrical charge. Now, it actually produces a lot more than that, but let's just say for the sake of argument. How much energy does the battery contain? So you're going to write down what you're given and what you're looking for. So it said 9 volts, and volts goes with voltage. So V equals 9 volts. The charge is Q. We're looking for the E. Okay, next, find a formula that has a V, a Q, and an E in it. And so that's, again, going to be this one here. And then put your numbers into the formula. Now this time you got to do some algebra. So you got to take the 100 over to the other side. So 9 times 100 is 900. And then what's the official metric unit for energy? It's the J. So stick a J on the end of it. Always, always, always put units on everything. Don't just give me a number, because if you're trying to take that information and tell somebody else about it, they may not understand physics. And so they won't understand what you're talking about unless you put units on everything. All right, let's take a break. And when we come back, we're going to talk about electrical materials.